Welcome to the technical seminar in thermal analysis. My name is Lani Celiz and I will be your presenter. Today's topic focuses mainly on pharmaceutical applications using simultaneous thermal analysis or STA, differential scanning calorimetry or DSC, and evolved gas analysis or EGA methods. The International Confederation for Thermal Analysis and Calorimetry defines thermal analysis as a group of techniques in which a property of a sample is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed. The physical properties evaluated by thermal analysis and their appropriate techniques are listed on this table. For changes in mass and the temperature difference between a sample and a reference material, the simultaneous thermal analysis or STA composed of thermogravimetry and differential thermal analysis method is used. For quantifying the energy in a reaction, the differential scanning calorimetry or DSC method is utilized. On the other hand, evolved gas analysis or EGA is a simultaneous technique for evaluating the kind and amount of volatile products released from a material. Here is an illustration of a TG curve indicating mass loss and mass increase, and how the common reactions are represented in a DTA or DSC curve, which are both plotted against temperature. By combining both TG and DTA or DSC, we can elucidate reactions such as the reactions listed on the table on the right side of this slide. Reactions such as melting, crystallization, glass transition, phase transition, dehydration can be measured by both STA and DSC. Other reactions such as decomposition, evaporation, sublimation, or water vapor absorption are recommended to be analyzed by STA. From this slide onwards, we will be introducing applications using differential scanning calorimetry or DSC. The applications for DSC are: in thermal analysis, selecting the appropriate type of sample pan shape largely affects the measurement results of a material. Here is a DSC application of benzoic acid using a crimped aluminum pan shown in blue curve and a sealed aluminum pan shown in red curve. Benzoic acid is used in food and in pharmaceutical as an active ingredient for antimicrobial and antifungal preservative. It is a subliming material, which means that the material changes from solid to gas phase. The crimped aluminum pan reveals a baseline shift towards the endothermic direction from 100 degrees centigrade due to sublimation, followed by another endothermic peak at 120 degrees centigrade due to melting. After the melting reaction, the DSC signal did not return to the baseline and it continues towards the endothermic direction due to evaporation. However, these reactions were not observed in the sealed aluminum pan except for the melting reaction. The use of sealed aluminum pan is effective in suppressing reactions such as sublimation and evaporation as shown in this application, allowing the measurement of melting in subliming materials. Sample preparation is essential to accurately obtain the significant thermal behavior of a material, especially when measuring with a small amount of sample. Disperse the sample thinly on the bottom of the sample pan as shown in the photograph. And if the sample are in different granular sizes, a temperature distribution will occur within the sample, which may result to a shoulder at a peak. In such case, after putting the sample in a sample pan, place an aluminum plate as a drop lid and lightly press it with tweezers to bring the sample into close contact with the bottom of the sample pan to distribute the temperature inside the sample. The shoulder may become smaller and it may disappear. If the sample has a shoulder in essence, it should be reproducible. So if there are cases where the peak is not reproducible, try preparing a sample in this manner. Mechanochemical methods such as ball milling or pulverizing have been used in the synthesis and preparation of a broad range of molecules and materials, including pharmaceuticals. However, it may cause an induced polymorphism, which may affect the bioavailability of an active ingredient. Here is a DSC application comparing non-pulverized or original and pulverized or after milling a pharmaceutical material. In the non-pulverized material, an endothermic peak near 60 degrees centigrade due to dehydration can be observed, and as the temperature increases, we can see another endothermic peak due to melting, followed by an exothermic peak due to recrystallization continuously occurring at 160 degrees centigrade. Finally, an endothermic peak due to melting is observed at 180 degrees centigrade. However, in the pulverized material, only the endothermic peak at 180 degrees centigrade due to melting is observed. Also, the dehydration behavior differs with the original material. The external application of mechanical energy causes physical changes known as mechanochemical effect, which may cause differences in measurement results. Caffeine is often used in combination of other drugs as stimulants, pain relievers, diuretics, cold remedies, weight control products, bronchial and cardiac stimulants, as well as in drugs for the treatment of skin disorders. We measured the thermal behavior of anhydrous caffeine using DSC from room temperature to 270 degrees centigrade. Results shows an endothermic peak near 160 degrees centigrade due to phase transition and a sharp endothermic peak near 237 degrees centigrade due to melting. However, grinding the caffeine for 3 minutes has caused a shifting of the phase transition temperature to near 150 degrees centigrade. Polymorphism in active ingredients can affect its bioavailability. Therefore, it is important to determine the thermal stability of pharmaceuticals. Here is an application on the phase transitions in different forms in sulfanylamide using DSC. In the gamma form shown in red curve, we can only see an endothermic peak at 164 degrees centigrade due to melting. However, in the alpha form shown in blue curve, we can observe an endothermic peak near 114 degrees centigrade due to phase transition. Similarly, the phase transition in beta form is observed near 119 degrees centigrade. Both materials exhibited another endothermic peak at 164 degrees centigrade due to melting, indicating that both materials have changed to gamma form. Since the glass transition is small, it often overlaps with other reactions and it disappears. For example, dehydration, crystallization, and enthalpy relaxation can be considered as phenomena that may overlap with the glass transition. When these reactions overlap with the glass transition temperature, the glass transition is measured by changing the sample pan or measure a second run, but the dynamic DSC, which is a modulated DSC, is also an effective means. In a modulated DSC, the temperature increases with a sine wave cycle. Therefore, the DSC curve has a shape with a sine wave-like amplitude and separates into a component that follows a sine wave and the other components. During this time, the component that follows a sine wave will be the component related to the heat capacity, which is called the reversible component. Reversible heat flow and glass transition appears in this reversible component. The component that does not follow the sine wave is called the irreversible component, non-reversing heat flow. Reactions mentioned earlier, such as dehydration, crystallization, and enthalpy relaxation, appear here. This is the measurement result of terphenadine with dynamic DSC. This was measured with a heating rate of 3 degrees per minute, a period of 36 seconds, and an amplitude of 0.43 degrees centigrade. Data analysis is performed using this data to separate the reversible component, which is the specific heat capacity component, and the non-reversible component, which is the other component. The result of modulated DSC in terfenadine is shown in this slide. Here, the reversible heat flow or the reversible component is extracted from the DSC result and separated from the non-reversing heat flow or the non-reversible component. When the reversible heat flow or the reversible component is confirmed, a slight baseline shift in the endothermic direction can be seen at 60 degrees centigrade, confirming the glass transition. In addition, in the non-reversing heat flow curve, which is the irreversible component, an endothermic peak is observed at 60 degrees centigrade, and exothermic peaks can be seen at 70 degrees centigrade and 110 degrees centigrade, which is similar to the conventional DSC result. Through these, even if the glass transition cannot be confirmed in the conventional DSC result, the specific heat capacity component can be extracted using the dynamic DSC and eventually able to confirm the glass transition reaction and glass transition temperature. One of the common problems in DSC measurement is the interpretation of results when unexpected peaks appear in measuring unknown samples. We can verify this through cycle measurement in DSC, but XRD DSC is the easiest way to understand regarding changes in crystal structure. In XRD DSC, the XRD data is added to the DSC information to determine whether the endothermic peak in the DSC is a crystal transition or melting based on the added XRD information. Recently, the use of sample observation DSC that records the live image of the sample during measurement is increasingly becoming popular, and it's often used to accurately interpret the results while looking at the image. This time, we will introduce the results of using the sample observation DSC for the thermal behavior of carbamazepine. In this slide, we will show the sample observation DSC result of carbamazepine Form 1. A 0.13 mg sample amount was used and heated at 10 degrees centigrade per minute up to 200 degrees centigrade. Results show that the exothermic peak is continuously observed immediately after the endothermic peak at 177 degrees centigrade. After that, another endothermic peak is observed at 193 degrees centigrade. Looking at the sample images at these peaks, the sample that was in a powder state at 170 degrees centigrade melted at 177 degrees centigrade, revealing change in shape and has partially become transparent. Then immediately at 179 degrees centigrade, the transparent part has changed to white, and we can see that it was crystallized. Therefore, we can conclude that the 177 degrees centigrade endothermic peak is a melting of Form 1 and then recrystallized into the high temperature stable phase. Also, from the sample image, we can clearly confirm that the endothermic peak at 193 degrees centigrade is melting. Here is the video of the thermal behavior of carbamazepine by sample observation DSC that I have discussed earlier. With the DSC Vesta, we are able to measure with sample observation option, UV irradiation attachment, or with other cooling options that allow us to measure at a wider temperature range that can correspond to different kinds of materials. From this slide onwards, we will be talking about simultaneous thermal analysis. The applications for STA are testing a sample using STA with an unknown thermal behavior for DSC measurement, mechanochemical effects in pharmaceutical, thermal behavior of carbamazepine, sample observation STA in trehalose dihydrate, and STA with humidity generator. When measuring a sample with an unknown thermal behavior using DSC, the STA method is a perfect tool for preliminary tests in confirming mass changes within the specified temperature range for DSC measurement, such as the application shown in this slide where caffeine is a material with unknown thermal behavior and the main objective is to use DSC for the determination of phase transition and melting of caffeine. So first we measured caffeine using STA. The blue curve shows the STA measurement result. It reveals an endothermic peak at 160 degrees centigrade due to phase transition and another endothermic peak at 236 degrees centigrade due to melting. It is followed by evaporation at 281 degrees centigrade. However, the TG curve shows that mass loss was initially observed from 170 degrees centigrade and that after the melting peak at 250 degrees centigrade, the mass loss is nearly 32%. With the STA result, we can set the conditions for DSC measurement. In this case, a seal pan measurement with DSC is recommended and the temperature range is up to 250 degrees centigrade. Please see the red curve. A seal pan is effective in suppressing mass loss reactions such as in this case, evaporation and other reactions such as dehydration or sublimation. The mechanochemical effect in pharmaceuticals does not only affect reactions such as phase transitions or melting behavior, but also shows a difference in thermal decomposition behavior of a material. In this case, the STA is the most suitable method. Here is a multiplot of STA showing pulverized and non-pulverized sulfamic acid. The thermal decomposition of a pulverized sulfamic acid starts at a lower temperature compared to a non-pulverized sample. Also, both samples show difference in exothermic peak height near 230 degrees centigrade. These results show the difference in thermal behavior due to mechanochemical effect when mechanical energy is applied to the sample by pulverization. The TG method is an excellent tool for compositional analysis. It is through this method that we are able to not only quantify the amount of water present in the material, but also obtain information on the dehydration temperature as well as the dehydration behavior of a material. Here is an application of the thermal behavior of carbamazepine dihydrate by STA. This was measured from room temperature up to 300 degrees centigrade. The STA result shows a mass loss associated with endothermic reaction at 62 degrees centigrade, which is overlapped with another endothermic reaction at 68 degrees centigrade due to dehydration. This simply means that dehydration has occurred continuously in two different stages in carbamazepine dihydrate, indicating a total water content of 9.8%. Then at more than 150 degrees centigrade, we can observe an endothermic peak due to melting, and increasing the temperature further led to mass loss due to thermal decomposition. Before we move on to our next application, I would like to introduce to you our sample observation attachment. Existing customers with Thermoplast Evo 2 STA8122 equipped with a standard furnace can later purchase the electric furnace with a built-in sample observation unit as an add-on option. With this attachment, the user can easily replace the standard furnace to a sample observation unit. Trehalose dihydrate plays an important role as an excipient and a stabilizer in the pharmaceutical industry. In this application, the sample observation STA method is used for the measurement of trehalose dihydrate. Here we can observe changes in volume, size, color, and shape as the sample goes through dehydration, amorphization, crystallization, melting, and at the same time, combustion. In STA, we can perform measurements under air static or with a gas flow using inert or air atmosphere. However, if you want to measure the effect of relative humidity on the thermal behavior of a material, the HUME-1 or humidity generator is a suitable option for simulation measurements using water vapor atmosphere. Here, the relative humidity can be controlled ranging from room temperature up to 85 degrees centigrade, dry to 90% RH with a maximum continuous operation time of 100 hours. This option can be connected to an STA, TMA, or even evolved gas analysis systems. So using the humidity generator or HUME option, there are two major measurements that can be performed. One is keeping the relative humidity constant at a constantly changing temperature, such as shown in diagram 1, or keeping the temperature constant at a constantly changing water vapor concentration shown in diagram 2. I will introduce another application using HUME STA on water absorption and dehydration behavior of alpha-cyclodextrin measured at a constant temperature with a constantly changing water vapor concentration continuously measured for 20 hours. At first, cyclodextrin was heated up to 180 degrees centigrade under dry conditions. Then it was cooled down and kept at dry conditions for 5 hours. Here, the mass loss is due to dehydration. When we increase the water vapor concentration, we can observe a mass increase of 11% due to water absorption. When we change to dry atmosphere, of the 11% absorbed water, only 6.5% mass loss can be observed due to the removal of free water and that the remaining absorbed water is bound water. Performing the same cycle showed the same results. Through these, we are able to quantify the amount of free water and bound water as the water vapor concentration drastically changes from dry to wet condition at room temperature. At the end of the measurement, the temperature was heated up to 180 degrees centigrade, where the strongly bound water was also removed from the material. Our STA system can be utilized as a standalone system that can be connected with a wide range of options such as sample observation unit, humidity generator system, and even systems for evolved gas analysis technique such as STA-FDIR, STA-GCMS, or STA-MS that suits your need. From this slide onwards, we will be talking about evolved gas analysis or STA-MS. This is a slide I have shown earlier. Here, the reactions in pharmaceuticals that are commonly evaluated by thermal analysis are listed on this table. Reactions such as dehydration, evaporation, decomposition, and sublimation or combustion are common reactions where there is a mass loss, and if there is a mass loss, then there is a simultaneous evolution of gases. Using the evolved gas analysis or EGA method, we are able to qualitatively and quantitatively analyze evolved gases. Through this, we can understand the kind of gases as well as their evolution behavior. An EGA system is divided into three major components. First, the sample is heated in STA for gases to evolve. Then the interface transports the evolved gases without condensation, And finally, the MS or FTIR detects the gases qualitatively. This is an example of an EGA measurement result. Here, the EGA curve is added to the STA data, all plotted against temperature. This is represented in the black curve where peaks indicate detection of evolved gases. A gas detector system can be an MS or an FTIR system. If the gas detector is an MS system, the total ion current or TIC curve is a sum of evolved gases detected as ions with relative abundances plotted against time or temperature. We can extract the mass spectrum in each temperature and compare it with a database library for identification. If the gas detector is an FTIR system, the total amount of evolved gases as infrared absorbance is plotted against time or temperature on a graph called Gram-Schmidt. Here we can extract the absorbance spectrum in each temperature and compare it with a database library for identification. The Japanese Pharmacopoeia has specified the use of TG method as a standard for the performance of loss on drying tests in pharmaceuticals. Here is an application of TG on the loss on drying test in epalrestat, a drug used for the treatment of diabetes. Using EGA-MS, we are able to qualitatively determine the evolved gases as well as their evolution behavior as a function of temperature. In our STA results, it reveals a 4-stage mass losses up to 250 degrees centigrade associated with endothermic reactions. Using STA-MS, we are able to qualitatively determine the evolved gases as well as their evolution behavior as a function of temperature. From the STA-MS data, we extracted the mass spectrum at 150 degrees centigrade and performed a search using the NIST library database. We have confirmed that the spectrum at 150 degrees centigrade matches with dimethyl sulfoxide fragmentation pattern in the database. And focusing on the molecular ion Z78, we have created a multiplot on the evolution behavior of DIMSO with STA mass losses, leading us to the conclusion that the multi-step mass losses in TG were caused by the evaporation of DIMSO from epalrestat. These are our available products in thermal analysis. Today, I have discussed with you STA8122, where you can measure from room temperature up to 1500 degrees centigrade. DSC Vesta, where you can measure from minus 170 degrees centigrade up to 725 degrees centigrade, depending on the cooling option. And Evolved Gas Analysis System with a commercial name Thermomass Photo, where you can measure up to 1000 degrees centigrade, equipped with a skimmer type interface and with electron ionization and photo ionization techniques available as a standard. Other products such as TMA 8311 as well as other hyphenated techniques in Evolved Gas Analysis and XRD DSC are also available. All these systems have a wide range of options that will provide solutions to your needs. We provide not only lectures and hands-on training sessions, but also live demonstrations on your samples for free. If you have some inquiries, you can send us an email on the email address provided in the slide. Thank you for your interest and for attending this webinar. We hope to see you again in our future session.